And it is also partially contained in the book, which is the second one, together with Wolfram Decker. So if those who are interested in could copy this literature, but anyway, I will give the slides of the talk to the organizers, and then you can download them. Okay. So we start with a finite group and define the commutator G1 to be the commutator of the group. That means the group generated by A, B, A minus 1, B minus 1 with A and B in G. And we repeat this process to define G of I. And G of I is a commutator of G of I minus 1 with the whole group. And then the definition is a group is called nilpotent if there is an M such that G of M is a trivial group. That's the definition of a nilpotent group. So examples, of course, abelian groups are nilpotent. If the order of the group is a power of a prime, then it is nilpotent. G is nilpotent if it is a direct product of its Sylow groups. So maybe I recall just what is a Sylow group. So if you have a finite group and the prime P dividing the order of the group, then you can choose M maximal such that P to the power M divides the order of the group. And a subgroup U of G of order P to the power M is called the P0 group. And these groups always exist, and if the group is a direct product of its Sylow groups, then it is nilpotent. And to see a group which is not nilpotent, that is S3, the permutation group of 3 elements. So let's just have a look to that. You can compute with magma, for instance. And in magma, you just define G as a group, as a symmetric group of 3 elements. And you define H, the commutator group of G and G. And then you obtain a group of order 3. And then you define again the commutator group of H with G. And you obtain again the group of order 3, so the same group. So the process stops, but not at the trivial group. So that means that the S of 3, the symmetric group of 3 elements, is not nilpotent. So that is magma. You just for the fun of it, you can do this with gap. In gap, you define the G to be the symmetric group of 3 elements, and then you take the commutator and you obtain the same result. or the second part of the slide, you can do it with SAGE, and in a similar way, and you obtain that it stops at the permutation group, at a group generated by 1 to 3, and that is not the trivial group. So you see there are a lot of systems handling finite groups, and you are invited just to try. Okay, another example is a dihedral group, D4, which is a group generated by R and S with the relations R4 is equal to S squared is equal to the neutral element, and the other relation is SRS is R minus 1. Now again, if you try a computer algebra system, you find out the dihedral group is a group of order 8, and according to what I said, a group of prime of order power of a prime should be nilpotent, and so this group should be nilpotent. So just let's try us. We compute the commutator group, obtain a group of order 2, and do it again, obtain a group of order 1, and so we end up to the trivial group, and that shows that the dihedral group is nilpotent. Now, there's a kind of a hierarchy. So the simplest groups are the abelian group. Next is a nilpotent group, and next now is the solvable groups. So now we define again the commutator GI by a commutator of GI minus 1 and GI minus 1. So there's a difference. Just you should see with in nilpotent we have the commutator of GI minus 1 and G, and that was G of I. And the solvable case, you take the commutator of the both subgroups instead of the commutator with a group with a whole group. So that the definition is again, if you end up after a while with a trivial group, then the group is solvable. Now, some examples. Of course, nilpotent groups are solvable. S3 and S4, the permutation groups are solvable. And then there's a big theorem. Groups of odd order are solvable. And that is a very complicated theorem with a proof more than 250 pages, and very important for this part of the group theory. And then you have S5 and A5 are not solvable. S5, the permutation group is of 5 elements, and A5, the alternating group contained in it. And here's just a reference to the paper of Veit and Thompson, where is a proof that groups of odd order are solvable. Okay, now back to computations. We try with a symmetric group S5. We compute the commutator group of S5 and S5, and it turns out a subgroup of order 60, and we want to know what kind of group is it, and then we ask whether the alternating group of 5 is equal to the commutator group of S5 and S5, and the answer, as you see, is true. And it is exactly given the elements of this group. And you can do it now with S4 to see that this is solvable. So you take the commutator group, you obtain a group of order 3, and if you do it again, then at the end you obtain a group out of order 1, and that means you end up in this process with a trivial group. Now, next group which we need is a PSLK. So that is a quotient of the special linear group. Special linear group are the 2 by 2 matrices with determinant 1. And we take the factor by the subgroup generated by the diagonal matrices. And then, for instance, PSL2 of F5 can be thought as a set of all classes of matrices with determinant 1. And in such a class are, in this case, exactly 2 matrices. And a remark which may be interesting, that the special linear group, the projective linear group, the PSL2F5, is isomorphic to the alternating group A5. So let us see this. Again, we define the group G as PSSL of 2, 5, and then we obtain the group of order 60, and then we ask whether this is isomorphic to the alternating group, and then the answer is true, and even the homomorphism is given, which gives us an isomorphy. So that's all done by computer algebra. Of course, you could do it by yourself, by hand, but it's just to see what is possible to do. And now it comes to a complicated group, so-called Suzuki group. So I mention it because it will play a role later on. So before being involved to the problem of studying solvable groups, I never heard about Suzuki groups. So that was probably will be the same to you. So Suzuki group is defined as follows. You take Q to be a power of 2. You consider an automorphism of the finite field FQ defined by theta of A is A to the power 2m plus 1, and that is the order of this field. And then you define 3 4x4 matrices in this way. And the Suzuki group is the group generated by these 3 matrices as a subgroup of the special linear group SL4 FQ. So just to get an idea what kind of groups are here coming on. And now we can start with a problem. And the problem is characterize the class of finite solvable groups by two variable identities. So abelian groups can be characterized by the identity xy is equal to yx for all xy in the group G. So then there is a result of Thorne from 1930. A finite group G is nilpotent if and only if there exists an n such that the Engel identity holds, and that means Vn of x, y is 1 for all x, y in G. And the Vn is defined in the following way. V1 is a commutator, and Vn plus 1 is the commutator of Vn and y. So that is something, so the result is about almost 100 years old, and so gives the characterization for the nilpotent groups. And what we wanted to do is a similar characterization for solvable groups. And we proved the following theorem. So now our identity is a little bit more complicated. So we define u1 of xy as x minus 2, y minus 1x. And un plus 1 of xy is the commutator of x un x minus 1 and y un y minus 1. And the theorem says a finite group G is solvable if and only if there exists an n such that the un of xy is 1 for all xy in the group G. And now let me make a remark which is very important for the rest of the talk. If you have x and g in the group G, and y is not x minus 1, and if you have u1 of xy is equal to u2 of xy, then never un of xy can be 1. So that means that gives you a possibility to check whether it is possible to obtain un of xy to be 1 or not. So if we want to prove that a group does not satisfy this identity, then we just have to check that u1 of xy is equal to u2 of xy. So that will lead later on to a system of equations. So now proof of the theorem. So of course, so one direction is very easy. If it is solvable, then the identity is true more or less by definition. So the other way around is a hard part, and we assume that the group is not solvable, and we have to prove that the identity does not hold. And now, what is the basis of our proof is a very important theorem of Thomson from 1968, classifying all simple, minimally not solvable groups. So Thomson gave a list of groups which are not solvable, and minimal in the sense that every proper subgroup is solvable. And that's why I explained PSL2. PSL2 is one of these groups. PSL2 of Fp, PSL2 of F2 to the power P, and PSL2 of F3 to the power P. P, a prime number, is in the list. PSL3 F3. And that's why I gave you an idea of the Suzuki groups. The Suzuki group is in this list. And what we have to prove for every group in Thomson's list, we find x and y in the group, y equal, not equal to x minus 1, and u1 of xy is equal to u2 of xy. And then we know for this group the identity will not hold. So that is now the problem. Choose any group of Thomson's list and prove that for this group there exist x and y in the group, y not x minus 1, and u1 of xy is u2 of xy. So what we will do here is a simple case. We take the group, the PSL2FP. These groups for p greater or equal to 5. So PSL2, as I explained, is a quotient group by the special linear group. So the elements are represented by matrices with determinant 1. So we take two elements, x and y, of this special form here. And then, of course, if you compute x minus 1, then it is 0 minus 1, 1t, which is obviously different from y, because y has at the first place a 1. So, and A, B, and C are parameters. No, B, C, and T are parameters. And they should run in the F3. And we have to prove that the equation U1 equals to U2 holds. That means there is a solution of this equation, and that means if we plug in these matrices over there, then we obtain equality for certain values of B, C, and T. Okay, now if we make the entries of the U1 and U2 are matrices, so we have 4 entries, and the equation gives us 4 polynomials to be 0 to hold. And now we have translated the group theory problem to algebraic geometry. Now we have a system of equations, and we have to prove it has a solution. So you compute the dimension of the system of the zero set defined by the system of equation. Dimension is 1, so it describes a curve. And we have to prove for every prime number p, this curve has a fp rational point. So the system has a solution. So here you just see how to do it in singular. You define the ring R to be the ring with a variable CBT, and you define the matrices and make this identity. The matrix M gives the relation, and then you take the ideal which comes from the entries of the matrix, that is by the command flatten, and then we get exactly the ideal which I showed you already before. Now what we need is a theorem which guarantees the existence of such a solution. And that's the theorem of Hasse-Weil, which says if you have a curve which is absolutely irreducible, that absolutely irreducible means it is irreducible under any field extension, and defined over the field FQ, you take its projective closure, and then there is an estimate of the number of points on this curve in terms of Q, the arithmetic genius, and the degree of the curve. So Hasse-Weil theorem says the number of curves of FQ is greater or equal to Q plus 1 minus 2 times the arithmetic genius times the square root of Q minus D. So what is the arithmetic genius? I explained before what is a Hilbert polynomial, and if you write the Hilbert polynomial of a curve, then it is a polynomial of degree 1 and looks as d times t minus pa plus 1. So pa is arithmetic genus and d is a degree. And for our curve, we obtain 10t minus 11. That means the degree is 10 and the arithmetic genus is 12. So now we try to have this estimate, and we saw that if the prime number is greater 593, then the number on the right-hand side is greater than 0. And so for all primes greater than 593, we have rational points on the curve. And the rest is brute force. You take prime by prime less than 593 and prove that they are curves, that they are points on the curve. So the important thing is to go from a set of infinitely many primes to a set of finite primes which you can handle with a computer. So what remains is now we have to prove that our curve is absolutely irreducible. So here, first of all, again, a computation. we have the ring, we take the ideal which we defined before, we homogenize it, homogenization of the ideal corresponds to the projective closure of the curve, and then we compute the Hilbert polynomial, and we obtain minus 1110. That is exactly what has been on the slide before. That's just how to compute this. And now the rest of the game is to prove that our curve is absolutely irreducible for all primes. So first of all, we simplify the equations, and we see that our ideal, which was generated by these 4 polynomials, is actually the quotient of the ideal generated by the 2 polynomials f1 and f2 divided by h squared. H is there. And so we could continue with the 2 polynomials to prove absolute irreducibility. So again, that is just how to show that both ideas are the same, that we can reduce to this case. So now we define the polynomial p, which comes from this reduction. And now we have a very concrete polynomial in x with coefficients in t. And we have to prove that this special polynomial is absolutely irreducible for all primes. So that is a very concrete question. So what you do in such a situation, you make an ansatz that it splits and proves that this is not possible. So we do this and obtain a decomposition and a system of equations for this decomposition. And then we have a system of equation, and to see that it has no solution. So a system of equations has no solution if the equation generates a whole ring. That's what we discussed yesterday too. So we have to prove that 1 is in the system of equations if I compute the Gröbner basis. So here are the equations. That's what we have to prove. So that these equations give the splitting of the polynomial, and if the set of equations would have a solution, then the polynomial would split in 2 factors. And if the system of equations has no solution, then the polynomial is irreducible. Okay, now using singular, we can prove that, I must make some remark before. We have to, let me go back. We have this system of equations, and we have to prove that for every prime, modulo prime, it has no solution. So, of course, you cannot compute it for every prime. So the idea is to compute over z and then move modulo the prime. And what we did, I will explain it in a minute, that we changed the kernel of singular a little bit exactly for this problem, that we compute over z and not canceling factors and so on. So keep all the time in the integers. And so the result is now in this situation that not 1 is in, but 4 is in. So 4 is in means that for every prime different from 2, the system has no solution. And 2 had to be settled in another way, so I don't want to talk about 2. So, but we were very lucky to see that we have a 4 over there, so we could cancel all the primes different from 2. Yeah, and that finishes the proof. Now we see, of course, now what I showed you, we have splitted the polynomial in 2 quadratic factors. Of course, you have to do the same thing with a linear factor and a cubic factor, which works similarly. So now let me just explain you again the idea. Now you can write in singular option content as B. And that forces singular to perform the usual Buchberger algorithm over Q without any division. So starting, that means, for instance, the S polys have to be multiplied up, and the whole computation works over Z. And that means the resulting Gröbner basis over Z is not a Gröbner basis over Z, but it's a Gröbner basis over Q, but you are able to reduce modulo P, and it will be a Gröbner basis over there. So let me show this in a very simple example. I take the ideal generated by 2x squared plus xy and 5xy plus y squared and compute a Gröbner basis. And the result is 5xy plus y squared, 10x squared minus y squared, and y cubed. That is a normal way to compute it.